This is the first chapter in Year 2 Statistics, and it's all about bivariate data. Bivariate data means data with two variables in it. So you're already familiar with bivariate data because you will have plotted a scatter graph before. So rather than just looking at people's heights, you might want to look at the relationship between people's heights and their weights. And you could plot a scatter graph to represent each person. Each point represents a person, and you know that you can put a line of best fit through there to look at what the correlation is. This chapter basically formalizes and looks in a little bit more detail at these scatter graphs. Before we look at example 1, we're going to go back to looking at exponential models, which is actually what you studied in Year 1 Pure. So in this example, we've got a scientist who's modelling the number of people n who have fallen sick with the virus within t days. And we're told that the model has this form. Now, if we were to sketch a graph of n against t, as long as b is greater than 1, then the gradient of this graph is going to get steeper. And it would have an exponential shape which looks something like this. And I could put a curve of best fit through it. The problem with this graph is it doesn't really help me work out what the unknown constants are, a and b. So often what it's useful to do is turn this exponential graph, exponential relationship, into a linear relationship. And the way that we do that is we take logs of both sides of the equation. So we'd get log n equals log of a b to the t, and we can use some log laws on the right hand side in order to get a linear relationship in t. So we could write that as log of a plus log of b to the t, and then we'll use a log law on the last term here and bring the t to the front. So we'll write it as t log b. So we get that log n is equal to this on the right hand side. And this is going to help us. Someone's already plotted a graph of log n against t for us. And we don't know whether all the points are on a straight line, but they've drawn a line of best fit for us. And the way that they would get this is they would take the original n values and they would just work out log of those n values to create a new table of values which they could plot. So let's forget about the fact that it's log n and t, and let's imagine that we had y and x. And what we're going to do is find out the equation of this straight line. Well, we know that the equation of the straight line will be y equals mx plus c. I'm going to change that to a capital X because I'm using a capital X. Well, we can work out the gradient of this line, m. The gradient is going to be the change in y, which is 2.55 minus 1.6, divided by the change in x, which is 10. And we can work out what that is, and we get that that is 0.095. We also know that the c in our equation is the y-intercept, so c is just equal to 1.6. So we could write the equation of this line as y equals 0.095 x plus 1.6. Well, at the moment, this doesn't help us find out what a and b are because we're not interested in anything to do with x and y. So let's replace y with what it's actually equal to. Y is log n because we plotted log n on the y-axis. So log n equals 0.095. X is what's on the horizontal axis, which is actually t, plus 1.6. So we get this relationship which we know is true between log n and t. And now there's two methods for finding out what the constants a and b are. So let's look at those two methods. So method 1 is the method that you will have used in the year 12 textbook, which is comparing this equation to this equation. Because we know that these equations are the same thing. They come from the same model. So if we compare these two equations, we've got log n on the left-hand side, and we've got something times by t. In this equation, we've got 0.095 times by t, and in this equation, we've got log b times by t. So if we compare the two equations, we know that log b must be equal to 0.095. And we can find out what b is, because remember that we're using log base 10. I've just not been writing it each time. So in order to find out what b is, we can do 10 to the power of both sides. So let's do 10 to the power of the left-hand side. And we'll do 10 to the power of the right-hand side. And the reason why we're doing that is because we know that 10 to the power of and log base 10 are inverse operations. So on the left-hand side we've got b, and we can work out a numerical value of b by doing 10 to the power of 0.095 to get b equals 1.24 to three significant figures. And we can also find out what a is, because here in this model, in this equation, we've got log a, and that corresponds to this part which is on its own. It's not been times by t, and that's our plus 1.6. So if we compare those two, we know that log a must be equal to 1.6. So log of a equals 1.6, and again it's log base 10, so we get that a equals 10 to the power of 1.6. So you get that a equals 39.8 to three significant figures. So that's method 1, by comparing the two equations that you get, one from the model and one from the graph. Method 2 just uses the equation that we got from the graph. So remember, we're doing log base 10, so we've got log base 10 of n equals 0.095t plus 1.6. Now we want an equation where n is the subject, because that's what we're looking for. N is the subject of this equation. So let's undo this log base 10 by doing 10 to the power of both sides. So you can have 10 to the power of log base 10 of n equals 10 to the power of, and then the whole thing on the right hand side. So 10 to the power of 0.095t plus 1.6. Well, 10 to the power of log base 10 of n, they cancel each other out, so we just get n. And we want to try and convert the right hand side into something that looks like a times b to the power of t. So the way that we can do that is we can split this power of 10 up. Remember, if we've got 10 to the power of a plus b, we can write that as 10 to the power of a times 10 to the power of b. So we're going to use that index law here. So we can write that as 10 to the power of 0.095t times by 10 to the power of 1.6. Remember, we're looking for an equation in the form n equals a times b to the t. And we've not quite got that here. It's clear that 10 to the power of 1.6 is going to be the a. So let's put that at the start. And then times by, and then we want something to the power of t. Well, notice that we could write this as 10 to the power of 0.095 and then put that to the power of t. So if we compare the model to this equation, you can see that this part is going to be equal to A, and this part in the bracket is going to be equal to B. So A equals 10 to the power of 1.6, and B equals 10 to the power of 0.095. And then you could work out a numerical value as we did in method 1. So you choose which method you prefer, method 1 or 2.